Okay? Okay. But I think it would be a good idea to start with chapter 4 because it's very conceptual in the sense that it brings a few new ideas into consideration. Remember that physics 1 to 5 is a non-major but still introductory course on physics where the idea is to introduce you in ideas of mechanics, and then obviously matter, energy, and then later on electricity, magnetism, and most likely applications in optics, and probably a little bit of introduction to very basic quantum physics and concepts of relativity if possible, right? Depends on the time and what I figure might be useful for you that you should learn, right? So we have already finished with chapter 1, 2, and 3. Again, I will go over the exam, okay, just to make sure. There are a few things. I think the major mistake was units confusion, not converting, but to realize the units of speed and acceleration. Other than that, I think that the concepts were clear, and I'm glad that that question about power, most of you guys knew how to do it. And then, well, we can discuss more about it, but I think in general, we're getting there, so that's good. So chapter 4 has a lot of new concepts, and then I will start adding the next chapters based on the notes here, right? We do have, by the way, let's share this so you can see it. Right? So we have finished this, and then there are no notes about what we're gonna be doing. So I will try to do the sample problems in class just to show you they are very simple about pressure, density, and buoyancy. Those are the main concepts that we're going to be discussing, but there are a few other things in there. And then, I don't know how many of you have watched these videos, but there are nice crash courses in here, and then there are demonstrations in here as well. I might start guiding you guys to go and take a look into those. For example, look, harmonic motion. We had Newtonian gravity here, Newton's laws, motion in a straight line. Okay, so I know that you may not have enough time, but they might serve better than just reading the slides. Okay, with the slides, I try to change them today a little bit so we can just have the main information about let's see if I have them here. Yeah, chapter 4. And again, it's probably gonna be finished on Tuesday next week with the problems. All right. And then we will have a few questions and answers. And we will have a quiz on this. I will let you guys know in advance when exam number 2 will be. The quiz on this chapter should be maybe next week or maybe the beginning of the week of Halloween. All right. We'll see. We'll see. All right. So let's remove this. Let's see how can I do this. Web Assign is good. So Web Assign is helping you. The extra credit is also helping you. So in terms of grades, you guys are okay, don't worry. But if you have any questions about your grade, we can talk after the class. I will see if I can finish earlier today, so we can do that. Okay. All right. Physics of matter. At the beginning, we're going to be discussing the 4 states of matter. There are 4, actually 5. There are only 3 that we really study in depth in physics and chemistry, especially in the non-major in an introductory course. But then you should know that there is plasma, and there is the Bose-Einstein condensed state. And then if you think about it, neutron stars, black holes, even white dwarfs, if you have heard of them, those objects in the universe, right? Those are exotic states of matter as well. But the ones that we know, right, the free states of matter plus plasma, we're going to talk about that. Forces a little bit, how they work. But the main ideas of today are pressure, density, and possibly I will try to introduce the Archimedes principle. And then from that point, we can talk about Pascal and then do a few examples. And at the end, I will just describe you. There won't be a problem on this, but I will describe Bernoulli's principle. I think it's a very interesting idea. If you like, in fact, just the other day, I had a friend from engineering asking me about pipes and fluids and pressure. It's interesting. It can be very interesting. So just as you can see there, you have a Zeppelin, right? And the most famous one, the Hindenburg from 1937, the one that crashed, remember, that was on fire. So nowadays, with the tools that we have, we can understand what went wrong in terms of like the physics behind the Zeppelin, okay? But just for you guys to know, when we talk about matter, it comes in 4 states. 3 that you already know from school, and the 4th one that is not really studied a lot in school, although we are introducing it nowadays, but there are not many things you can do in the lab with it. That's why we normally introduce what? Solids, liquids, gases, and the 4th state, plasma. Now, plasma is very important for physics and astronomy because a plasma has properties of a gas, as it says, as it's in the book, right? It conduces electricity, and it's basically a superheated gas, right? The best way to describe it is when you look at the sun. The sun is not solid, right? It's not a gas. It's basically a superheated gas that is plasma, right? So it can be very dense, it conduces electricity, and it's normally really, really hot, right? That's plasma. But for all intents and purposes, we are going to be doing more, we're going to be discussing more about solids, liquids, and gases. So a solid is basically like anything that you are observing, where you're sitting, where you're touching, is a solid, right? A liquid, well, water, it has a flow, right? It has a well-defined boundary, surface tension, viscosity, and has a higher density than gas. A gas has a very nice flow. It takes the shape of the container. It doesn't have a defined surface, obviously, and it can be easily compressed. You can squeeze it, right? If you have a container and a piston, you can compress it. The difference is about the microscopic composition. So normally the way we say is that a solid is rigid. So the particles are in fixed positions. Now we know nowadays that there is vibration. One of the reasons we study harmonic motion is because the molecules that can be arranged in the structure of a solid, right? They are rigid, but there are small oscillations, very tiny oscillations, all right, almost negligible. And they have a fixed form and shape, right? With the liquid, however, the particles are more spread. Not spread enough to be like a gas, but they are more spread, all right? And then in a gas, the particles are all over the place, okay? The distances are 10 times or even more times larger than the difference between the particles in the liquid, and they can be moving at very extreme velocities. So that's basically the microscopic view of the 3 main states of matter. And then with the plasma, you start having supercharged particles due to the enormous amount of heat, and that's the reason why it can conduct electricity so easily. So that's there, right? That's the summary here of what I was talking about. Now, for the plasma, all right, as I said, in your everyday experience, you can see matter as solid, liquid, or gas. But plasmas, maybe not, they are rare. However, you can see some of these in the case of the fluorescent light, right? Where you have a glowing plasma in there. That's the reason why it's so shiny, okay? But I think the best example is when you look at the stars, all right? That's one of the goals that we have in physics, is to produce a very large version of a star. Like, if you think about it, right? The future for energy on Earth is not oil, it's not fuel, it's not solar energy or wind energy. It's nuclear energy, but the safest and more clean way to produce energy that we can use to transform into electricity to illuminate, right, a whole city or a whole state will be energy using nuclear fusion. Okay, so you can basically reproduce what's happening in the core of the sun. Anyway, so there are cases where you have substances that are not very obvious what state they are. For example, when you have granulated sugar, right? That's solid, but it takes the shape of the container, right? But that's because of when you analyze a single granule of sugar, it's solid, right? It's just very tiny. Then you can have there other type of, like for example, very dense. That's like what? Chocolate, right? Like chocolate cream, and it's actually liquid, but when you put it in a spoon, it looks like a solid, sort of like a wavy, sort of mushy solid, right? But it's actually liquid, okay? So there are substances out there who may not really fit any of the states, but if you are strict about their composition, you can easily know what is state. So it's just an extra piece of information there. Now, we have to think about the conditions for a substance to be in a given phase. Look at that container, right? To produce that, what I can do is I can have ice and water, and then I can let it melt. And even if I want to do it faster, I can let it melt in a very warm surface. Let's suppose I put that container with icy water in a sauna. Something like that will happen, right? You will have the ice, or in fact, probably even the steam room, which actually is warmer than sauna. So, or if you are putting in a stove. So obviously, the ice will melt into water, and then the water will melt. The water will will boil, right? Will vaporize. So water is normally liquid, but it becomes solid at 0 degrees Celsius, 32 Fahrenheit. But that's under normal pressure. That's normally standard conditions, all right? Now, when you boil water, you are increasing its temperature, and then you are changing the phase of water from liquid to gas. So you can have the three phases of water in there. The gas, a little bit of chunk of ice still remaining, and then the water due to the melting of the ice. Now, very important to think about the pressure and the conditions where this is happening. If you think about it, or you probably have heard about this, the conditions for water to boil are different depending on the altitude. If you go to, for example, I'm from Peru, and I've been in the highlands, and because as you go up, the pressure is less and less. As you go up, and we're going to talk about that today, as you go up, as you climb a mountain, the pressure is less. The amount of oxygen is less. So water might boil faster in that scenario, in that case. all right, because the pressure is less. Okay, so we have to think about those conditions as well. All right, so that's a phase. And the thing about phases of matter is that when we talk about phases, we talk about the macroscopic property of matter, what you see. So right now, that's in liquid, right, what you're seeing there. So in science, we will be talking about matter in one pure phase. Solid like a rock, liquid like water, gaseous as carbon dioxide or air or steam. All right? So when you say that there is a substance like water that is in a particular phase, that means that phase is happening at normal room temperature. Normal room temperature is around 25 degrees Celsius and 1 Pascal of atmospheric pressure. So that's the unit for atmospheric pressure. Remember that we are on Earth and we're surrounded, not surrounded, we're in within the atmosphere, right? We live in the troposphere. But there is the stratosphere, and then you have the ionosphere, right, and the exosphere. So in the layer of the atmosphere where we are, we can say that the atmospheric pressure is approximately 1 Pascal, right? Oh, somebody left a call. Who is that? Okay. So 1 Pascal is approximately, well, we'll talk about that. Sorry, 1 Pascal. 1 atmosphere. 1 atmosphere is approximately 100,000 Pascals. Pascal is the SI unit for pressure. Atmosphere, because we don't want to be talking about 100,000 Pascals, right? So in the scale that we use, for example, in the lab, we use atmospheres. The scale that we use here in the US for pressure, for example, when you want to measure the pressure of a tire in the gas station, they use PSI, right? So PSIs, and in hydraulics, they also use PSIs. That's an imperial system unit, okay? But again, just to let you guys know, in normal conditions of room temperature and pressure, that's when we have water phase liquid, right? Water at liquid phase between 0 and 100 degrees Celsius, okay? That's 32 and 212 Fahrenheit. Guys, what you're seeing there is the structure of the atom, but unfortunately I have to say this, that's not really the correct one. I mean, that's the one that we show even in middle school and in high school, in chemistry 1. And that's because it's a very easy one to understand. If you have done chemistry before, or probably in school, I know you did in school, right? You probably talked about the Bohr model of the atom, where you have the hydrogen atom, right? And then you have 1 proton and 1 electron going around it in circular fashion. So we know now, or after Bohr introduced that model, it was corrected to the point that it wasn't really it wasn't really a circular motion, but it was better to talk about orbitals. So that's why we say that the electron is orbiting around the nucleus of the atom. The nucleus of the atom is a point of biggest or largest density. That's where most of the mass of the atom is concentrated, because that's where you have the protons and the neutrons. The protons are approximately 10,000 times more massive than the electron, right? So that's why and neutrons as well. So that's why we say that most of the mass of an atom is concentrated in the nucleus. Now, what's wrong about that model is what you're seeing there, basically. We know that electrons are on the outer shell, or in sort of like orbitals, but they're not really orbiting like planets around the sun, the nucleus. The correct model of this is having an electron cloud. An electron cloud gives you the probability of finding the electron where it's pointing. All right? So that was introduced by the Schrödinger equation and by the Heisenberg uncertainty principle. So again, those are concepts that go a little bit beyond the scope of this chapter, but I think it's a good idea that you know that electrons don't really orbit the nucleus of the atom, but they are in an electron cloud, right? And then we analyze the probability of finding the electron at certain position or at certain speed. That's why the Heisenberg uncertainty principle is telling you that as the probability of finding the electron increases, the probability of knowing the momentum decreases. And what is momentum? Mass times velocity. In other words, you may know a lot, you may be able to get or gather information about the position of the electron, but you will decrease, you will not know as much about the motion of the electron, the speed of the electron. So that's the problem, right? Now, that's interesting, right? Because we have a model that works, and we have a model that let us understand how matter behaves. Now, when we talk about atoms, we need to remember that everything, the basic unit for matter are the elements, right? And the basic unit of an element are the atoms. So we can have atoms of hydrogen, of helium, of carbon, and so on. Now, when we started to discover these elements, we knew we had to start, we needed to find a way to gather this information, to analyze this information. So at the beginning, we thought, well, how about if we do it by the phase where we find them? But guess what? We can find some of these elements in different phases, right? And as you can see there, it's probably not going to be good enough. Then they gave the idea to do it by the atomic mass. But it didn't really work out. It was kind of a mess. The best way to organize the elements is by using the atomic number, which is the second column that you see there. The third column, right? This one. And as you can see, now it makes more sense. If you have a periodic table with you, you know that a periodic table is arranged by groups and periods. You have the columns, which are the groups, and you have the periods, which are the rows. And the element in group 1, period 1, the first element will be hydrogen. And then you will have lithium. Now you're probably thinking, well, what about helium? The second most abundant element in the universe. Well, helium has a property that makes it a very interesting gas. It's a noble gas. So we have our own separated column for noble gases. On the other extreme of the periodic table, helium, neon, argon, xenon, krypton, all right, neon. So all of those are noble gases. And then we divide the periodic table by metals, non-metals, by radioactive elements as well at the bottom, all based on their atomic number. Okay? There. Look at this, right? When you look at an element, group 1A, period 1, you have the atomic mass, you have the atomic number 1, and that's the way it goes as you go from left to right. Right? 1, 3, 4, 2. Then you go 20, 21, 22, 23. And the noble gases are here. There is a section, I'm not a chemist, but there is a section for the alkaloids, alkalines, right? You probably have heard about that. In chemistry, we need that. Because in chemistry, we talk about bonds. Ionic bond, covalent bond, So a metal and a non-metal, normally they give you a covalent, right? And you can have two types of molecules. You can have a polar and a non-polar molecule. So there is your composition of water. Again, I'm not going to go into the chemistry of how these atoms get together in bonds, how the bonding works, but just remember that there are some molecules out there who are joined together by chemical bonds, and these chemical bonds can be different, right, depending on the nature of the elements. Now, we also have chemical compounds, which are the simplest form of everyday matter. Okay? Compounds are very similar to the elements, guys. And they have a unique building block, which is a molecule. So a compound is made of molecules. All right? And every molecule of a particular compound has the same unique combination of two or more atoms, like the one you're seeing there. All right? Some examples of forms of matter in there. Of course, there are different compounds, and the compounds normally are represented by a formula. All right? So we have the number of atoms of hydrogen, H2O1 or O. There is just one atom of oxygen. So water has two atoms of, that's the composition of water, right? Two atoms of hydrogen and one atom of oxygen. And then you have other ones, carbon dioxide, carbon monoxide, okay? Again, guys, this is just an introduction to the composition of matter and a little bit on the chemistry behind this, right? Now, in the case of the forms of matter, remember that we can have matter, right? And we can classify them and have substances, such as air, stone, water, seawater, right? That they are composed, or seawater actually, not fresh water, seawater. Because there's a difference between the water that we just saw, right, the compound, and the substance, seawater. Seawater is a substance because it's made of two or more different compounds. In the case of seawater, it's water, normal water, and minerals, even salt, right? So you combine them and you get seawater. Air. Air, you are seeing there the composition of air. Nitrogen, most of it, 78%. Oxygen, 21% basically. And then you have argon, carbon dioxide, etc. In fact, people normally ask, right? Because when we talk about climate change and stuff, the most common compound that we talk about is carbon dioxide, right? CO2. CO2 is actually a very important gas. It's a greenhouse gas. A greenhouse gas allows the Earth's atmosphere to capture and retain heat. Now, that's not the biggest greenhouse gas. It's actually water vapor. If you guys go and take a look on the bibliography about the composition of the atmosphere, you will see that after argon, the compound that is the most abundant is water vapor. Water vapor, right? Vapor. Carbon dioxide is also, relatively abundant. If you compare it with the other gases like helium, neon, and so on. But we're not exactly sure how, or we can see it, right? We can see climate change happening, but we're not exactly sure how carbon dioxide is affecting or our production of carbon dioxide, right? We have to figure that out before it's too late, though. Okay? But it's important to study this So you can know that carbon dioxide exists in the atmosphere. It's just that it's only 0.03%. Okay? In comparison with oxygen or nitrogen, it's almost nothing. Now we can talk about mixtures. A mixture of two elements is not the same as a compound, all right? If you mix hydrogen and oxygen, you may have a gaseous mixture, all right? In order to have a compound, you need to have a proper combination of the elements, all right? So if you ignite a mixture, then you will have hydrogen and oxygen combining to form water. The best way to analyze this, guys, is if you guys watch the movie The Martian. When the astronaut was stuck in Mars and he decided to raise potatoes, right, to eat, to breed potatoes, right? He knew that he needed water. There's no water in Mars. Well, I mean, we know that there might be in the poles or maybe underground, but it's running solid ice, and he didn't have the tools to explore. And anyway, it was too much of like a risk. So he needed to find a way to produce his own water, right? So he ignited the mixture. If you remember that scene where he explodes inside the space base, inside the base where he was, he explodes in there where he was trying to produce hydrogen. Oxygen there was, because that's what you breathe. But when you are maneubrating with this, hydrogen is very explosive. We have the hydrogen bomb, right? So when he tried to create water, right? At the beginning, it wasn't successful. He needed to find a way to calibrate the temperature values and the ignition, okay? And the excess of oxygen. Now that was the problem, I remember. There was an excess of oxygen, so he needed to isolate the area. Anyway, all it is, energy is released explosively in the form of fire. There you are. So that's the explanation, basically, of what happened in that, right? Now, the basic unit of life is a cell. The basic unit for matter, remember, is the element, okay? Now, let's talk about the behavior of atoms and molecules. That's what I was talking about at the beginning. What's the difference between a solid, a liquid, and a gas? A solid, there are attractive forces. We normally call them intermolecular forces, Van der Waals force, for example, or London forces. They are forces between particles. They get weaker as you are going from solid to liquid, and then way weaker as you go to gas, because they cannot really bind them together, okay? So in a solid, the forces are very strong. In a gas, they are very weak. This is what we know as the standard model to represent the interparticle forces in a solid. As I was saying at the beginning, right? Even though we accept the fact that atoms are in a fixed place in the solid, as you see in part A, in part B, they sort of recreate very nicely what's actually happening. So it's sort of like each atom is connected to a spring, and at the same time is connected to a neighbor. The atoms are free to oscillate, like we did in the simple harmonic motion, or the mass oscillating on the spring. But the oscillations are very, very tiny. And on the other hand, right, in terms of the shape, right, many atoms or molecules in a solid, they form a regular geometric pattern called a crystal. We call that a crystalline solid, where the atoms are in fixed positions and they have a nice shape. All right? If they don't have a crystalline structure, then we call them amorphous solids. All right. So either a solid is crystalline or is amorphous. All right. Any questions so far about matter, compounds, molecules, the states of matter? Any questions about what's a crystalline solid? You're basically seeing them, right? Remember, a crystalline solid is a solid again, where the atoms are in fixed positions, like shown in the screen there. All right? And even though they are in fixed positions, we can still say that they are interconnected by a spring, all right? And that they can still have very tiny oscillations, all right? Look at the diamond structure. Now, that is a structure of carbon, all right? So there you are, right? It can have different properties and different bonds in there. It's very important to understand the symmetry and geometry and geometry of the carbon atom, because remember, our organic life is based on carbon. All right, so it's one of the main elements here on Earth. For a liquid, again, the forces between the particles are not very strong, so that's when you start seeing them moving away from each other. The forces between particles are normally responsible, guys, for the surface tension. The surface tension is the reason why a mosquito can't step on the surface of a lake. A mosquito normally can't do that. That's because of the surface tension, right? It's sort of like the mosquito is taking advantage of a very weak, thin, tiny layer on top of the water on a lake. And also you can say in between of the air surrounding it. It's like a halo. And because mosquitoes are very tiny and very small and very low, almost no mass, they can't step on it. Looks like they are walking on the water. They are not. And it doesn't always happen, but it happens. And that's because of surface tension. Okay. And that's a gas. In a gas, the atoms and molecules are more separated. And they can travel at very high speeds, as I mentioned. In the case of the oxygen molecules, they can travel at speeds of approximately 1,000 miles per hour. Okay? And they collide. And remember when we talk about collisions in the last chapter, right? Ideally, when we talk about an ideal gas, we assume that the collisions are elastic. That means that there is no loss of energy or momentum. Momentum, you know, it conserves. But there is no loss of energy either. Okay? Well, this one is showing you how you can easily compress a gas as you apply an external force. That's because of the large space between the atoms in there. Okay? So we can easily compress a gas because of that. Because of the very large distances, in some cases, in between the atoms. Okay? Now, just as a summary, there are 118 different elements we keep discovering. Okay, so don't be surprised if we found one more this year. Molecules, 2 or more atoms stuck together. Okay, the forces between the atoms, molecules, they determine the state. Okay, then we have compounds. the basic unit for a compound is a molecule, and then we have a mixture and a solution. A mixture or a solution can be homogeneous or heterogeneous. You probably have heard about that, right? And you can do them in the lab. Lemonade, for example, is a nice mixture there. All right? Solutions, you can make them in the lab, in chemistry. All right? And that's just a combination of different elements and compounds. All right? For example, sulfuric acid. Or any mixture that you do or that you buy to clean a house. Sanitizer, right? That we've been dealing with that thing in the last few months. Sanitizer can have different percentages of alcohol. And depending on the percentage of alcohol, it can be good or bad to clean a surface, or it can be effective to clean a surface, right? So you have a mix there. And depending on the mix, you have a percentage of alcohol in there, right? The more alcohol, the better the sanitizer. I think it has to be around 96% to be effective. Anyway, that's a nice flow chart. So if you get to the slides, I want you guys to read that or to maybe write that down. You have the phases of matter, the four main phases, and then the descriptions of each phase. All right? Okay. Let you guys answer the following questions. What are the three common phases of matter?
Liquid, solid, and fluid. No.
Liquid, solid, and?
Gas.
Gas, exactly.
Okay.
True or false? The number of protons in the nucleus of an atom determines which element it is. I'm going to give you the hint. The atomic number is the number of protons and electrons in an atom.
True.
True, yes. Right, as I said, to know what element you are dealing with, you need to know the number of protons. Right? That gives you the atomic number. If you have the atomic number, you can do what? The electronic configuration. Again, that's more chemistry, but if you have seen chemistry, you know what I'm talking about. The molecule is a basic unit of what?
Element?
No, element is the basic unit of matter.
Oh.
Sorry, of like in the periodic table, right? Element is the basic unit. But for a molecule, which is a combination of two or more elements, the basic unit for a molecule is, no, the basic unit of a compound is a molecule.
Okay.
Okay? True or false? Air can be compressed easily because there is a great deal of empty space between air molecules.
True.
True, yes, very good. All right. Let's use the board for this. So we've already introduced the idea of composition of matter, right? But now I want to introduce the idea of pressure and then density. And then we can go into the slides. Okay. Okay.
Good.
It's too small. Let me see. Okay, so when we talk about pressure, think about everyday life as well. When you are sitting on a chair, when you are leaning towards a table or anything that you do, we talk about forces, that's fine, like the force to push or to lift something, right? When matter falls, like an apple falling from the tree, that's the force of gravity acting, right? We talk about normal forces, the friction, but in everyday life, we talk or we refer to many of those instances as pressure. Pressure in the cabin, inside an airplane, atmospheric pressure, pressure as you go up when you climb a mountain, or as you go down if you are doing diving, right? Or if you are in a pool. So pressure is a very nice way for us to understand or to deal with everyday life situations. So it's basically the force exerted by gases, liquids, and solids, but spread over a surface. The best way to understand this is by drawing a surface. And then drawing a force being applied towards it, on top. So we know that force is a vector, that's fine. But pressure is actually scalar. And we can say that pressure P is equal to the force divided by the area in units of newtons per meter square. All right? Now, when you are walking, right, as you take steps, there will be a pressure due to your shoes on the floor. And as you're standing, then the pressure may be even more, in some cases double, because the pressure on each shoe, right, due to the fact that you are stepping on the surface, is divided by 2, right? So it's equals on each side. Now, when we talk about pressure, it's also a good idea to introduce the pipes. In everyday life, we use pressure in pipes, in airplanes, right? When you are doing sports, for example, in diving, okay? Even when the weather changes, when you look at the weather channel, they will give you the pressure, humidity, all those are factors that affect the environment, right? Not just temperature by itself. So that's the equation for pressure, is the force per unit area. Now, what is the only condition for that formula to hold? The force needs to be perpendicular to a surface. So here, that force is perpendicular to a surface. All right? Can you find the pressure if the force is at an angle? Yes, but you will need to break it into components, right? To find the perpendicular component acting on the surface. If I do my hand like this, I don't know if you can see that, right? If I put my hand like this, I'm not even resting it, I'm just putting it like that. There's no force, right? If I put it like that, there is pressure, right? Now, there is a lot of applications on pressure in gases, more than solids, right? And there's also applications in liquids. And we will see that it does have to do with the fact of how we define a solid, a liquid, and a gas, in terms of the particles moving and the composition of it. Now, I introduced you those units for pressure. Normally we call that a Pascal. So for the weather, right? Let's talk about the atmospheric pressure. So when you look at the weather, they should give you the atmospheric. So anything, regardless where you are always being, you're always gonna feel the atmospheric pressure due to the, well, the atmosphere, the gases in the atmosphere. This pressure is equal to 1 atmosphere, which is also equals to 1.01 times 10 to the 5 pascals. And these pascals, right, 1 Pascal is basically 1 Newton per meter squared. It's just that we define this for everyday purposes. But that's not the only unit of pressure. You can also have pressure in millimeters of mercury. You use that a lot in chemistry, or in PSI. PSI is a very common unit used in hydraulics. This is approximately, or exactly, sorry, 6,890 pascals. It's a lot. That's the imperial unit of pressure, PSI. In machinery, you will find it a lot. All right? And okay. There are a few values for pressure. For example, as I said, the pressure in the average sea level is 1 atmosphere. But for example, the pressure typically inside a tire is triple that, right? In the case of the center of the earth, right? As you go towards the center, the pressure gets bigger and bigger in the order of millions atmospheres. So we do feel some sort of pressure, but as you go towards the center, which is the reason, so a lot of people always wonder, how come we've been able to travel to the moon, and hopefully soon enough we will be able to travel to Mars, but we haven't been able to dig a hole towards the center of the planet? There are 2 reasons. First of all, because the mantle of the Earth, because we actually live on the crust, but then, if I remember, it's around 50 kilometers or less than that. It's very thin. But then you have a big chunk that we call the mantle. That mantle has a way different composition than the rocky stuff that we see, for example, in the Grand Canyon, right? It's very, very dense. And it's also subject of an enormous amount of pressure. As you go towards the center or inside the Earth, the temperature and the pressure especially increases almost exponentially. So that makes it very, very difficult to dig a hole and just go, right? And then once you go beyond that, because you are going to go through tectonic plates, the mantle, then you can go into what we know as the outer and inner core, right? So that I don't think would be possible. I think there's a movie about that. It's a very, almost 20 years old, that they talk about going to the core of the planet, and they actually explain a little bit of why it is very difficult to do it, right? But in any case, the center of any planet or star has an enormous amount of pressure. For example, in the case of the sun, it has billions of atmospheres. And remember, 1 atmosphere is 100,000 pascals. So that's a lot, right? That is a lot. Okay, so what type of problems you can be asked? Look, in the slide they give you a problem with pounds and square inches. So that is a problem where you will have the pressure in PSI. PSI, as I said, are the units in the imperial system. So if I give you a force, let's say a weight, let's say that let's say my weight It's actually not that, but let's suppose the weight of a person was approximately 160 pounds. And the area where that person is standing is approximately 20 square inches. 20 square inches, like that. So if I calculate the pressure using the formula, the pressure will be 160 divided by 20. That will be 8 psi. The thing about this is that if I was doing with SI units, my force is in newtons, so I cannot use just the mass of a person. I have to find the weight and then divide by the area, not in centimeters square, but in meters square. All right, so that's important there. Okay, so let's suppose you want to find the outward force acting on a passenger window on an airplane. All right, let's suppose now that they give you the dimensions. Pressure acts in every direction, by the way. So the atmospheric pressure, when you feel it, is acting all over, right? So if you are traveling and you want to measure the force that an airplane window is withholding, all right, it might not be very accurate because I want to use 6 psi as the atmospheric pressure. And let's look at a table here. So okay, as you go higher, the pressure is less and less. The atmospheric pressure actually at sea level is 14.7 psi. That's in your table there in the slides. But as the airplane goes up and up and up, the pressure is less and less. So let's suppose we can accurately say that the pressure can be approximately 6 psi. All right? So even less than 1/2. So if you have that the pressure is 6 psi and a window has an area of 1 foot by 1 foot, let's find the force acting on the window. Force is pressure times area. Perfect. So I need to find the area, but remember that psi is not with feet, it's with inches. 1 feet is 12 inches. So the area is 12 inches by 12 inches, 144 inches squared. So my force will be the pressure times the area. Right? And I believe you get 864 pounds. It's weird, right? Because many of you measure your mass and you get pounds. Remember when we talk about the difference between mass and weight? Kilograms and newtons, right? Now, how will I get that value into newtons, right? I will have to find the atmospheric pressure in atmospheres, change it to pascals, and then multiply that by the area in meters squared, right? But let's continue talking about this, so at least you know how to do the basic calculations there for pressure and force in there, if you're given the pressure, okay? Let's talk about gauge pressure. So applications on every day. That one is important because you deal with that when you want to change a tire. In fact, I have to deal with that in a few days because my tire is has low pressure right now. So when you guys have a gauge, we call that a gauge pressure, and you measure 30 psi, that actually is the pressure difference between the inside and the outside. Your pressure has to be approximately 30 to 25 more than the pressure outside. So if the pressure outside is around 14, and it makes sense because the atmospheric pressure is around 14.7 psi, 1 atmosphere. So when you measure the pressure of your tire and you get 30 in the gauge, you know that the real inside pressure is the gauge pressure that you measure plus the atmospheric pressure. It's sort of like if I have a container, right, and I open it. Let's suppose there is a water or gas in here, right? The pressure that this guy is feeling actually, yeah, let's suppose you have like a device here and you are compressing it, all right? But it's open. The pressure that the gas is feeling will be the pressure that you exert plus the atmospheric pressure. All right? Atmospheric pressure is a constant. Sorry, it's not really, right? But it's a value that we have to take into consideration. Why is not really a constant? Because it changes with height. And that's clue, or that's key for what we're gonna do. All right? When we talk about pressure, we need to consider that pressure varies with depth. All right? Look, I can actually show you that very quickly and then we can finish with that and we can talk about the exam. But pretty much, let's suppose you have a container. All right? So now we're going to introduce that idea of density. And density. Actually, no, we will do the equation next class. Let's talk about density right now because it's gonna be important for pressure. All right. So just to finish today, we're gonna leave it there in gauge, pressure, and PV, the Boyle's law. But just remember, for the upcoming class, we define pressure today, but also we're gonna define density. Density, the symbol for density is actually this one here that you're seeing. That's called rho. Okay? Rho is the symbol for density. Okay? There. Okay? Now, what the definition of density is equal to the mass divided by the volume of an object. So the units are normally kilograms per meter cube. So these are the two parameters that I wanted to introduce today. All right, we talk about pressure, gauge pressure, atmospheric pressure, and then we're going to talk about density because when we talk about liquids and gases, density is very important, right? Water has density, air has density, and then depending on the density difference, now we can understand things like why a helium balloon goes up. when you leave it in the environment, right? But what an air balloon, why an air balloon stays on the ground? A helium balloon goes up. So we will talk about the density differences and the buoyancy. But for that, we need to understand this, pressure and density. All right, so those are the main concepts. We can keep talking about more of this next class when we talk about, density. We start with mass density, and then we can introduce the formula or the equation for pressure as a function of depth, right? Pressure, as you go deeper, increments. There is an equation for that we can use in real life. And then we can talk about the barometer, which is a device that we use to measure atmospheric pressure. Okay. All right. The exam. The only mistake that I noticed a lot, the main one, sorry, was this. A lot of you guys use this as acceleration. You have the mass, and then you said 5 times 10, 50. So, not really, right? The acceleration here was just 10 divided by 2. Because it's the change of speed, 10 minus 0, divided by the time. So, one clue about mathematics and physics, at least for these type of problems and for introductory courses, right? Algebra happens in algebra, happens in trigonometry, but also happens in physics and chemistry. When they give you a piece of information and you don't use it, you have to go and double check the problem. Because normally, 90% of the times, the information that they give you, you need it. So you didn't use the time. So then there was something wrong, right? But you needed it to find the acceleration, and then the force was 25. Because that was the acceleration. So this was the acceleration. Okay? If you have the acceleration, then that's it, right? And then second square, the units, right? So then the force was 25 newtons. And then the work was force and distance. The distance was just 1/2 acceleration times time squared is how much? 4. So that was 10, I think. Yep. And then the work was just force times distance, 215. And this mistake was repeated. You guys did all was fine. You guys did this fine. This was okay for everyone. Here, you guys did the kinetic energy. Good. We did this running in class, right? To find the value of the force, you needed the mass times the acceleration. Many of you did this times 30. No, the acceleration here was again 30 divided by 5, 6. If you got the acceleration, the force was 1500 times 6, 9,000 newtons. And then the kinetic energy, everybody got that. The work done by this force, you had to do exactly the same. 9,000 times distance. And the distance, you had to use kinematics for that. By the way, they were the same. The initial kinetic energy was the same as the value of the work done by the force. So the work done by the force has to be enough to stop the car. And if the car has some energy, you need to do enough work to hold the energy there. That's it. Kinetic and static friction, okay? You did this question. The skaters problem we did in class. I think some of you got it, some of you remember, was mass times velocity times one, or proportions, right? If the 55 kilogram skater is being pushed at this speed proportions, huh? If 55 is being over 70 equals to 0.6 over x. That's what you have to do. Actually, like this. It's a inverse type of proportion, so that's why. Okay. For the Galileo experiment, I was looking more to the fact that it cannot be replicated on Earth because of the air friction. Gravity is not a factor. There is gravity on the moon. So you can't do it on Earth if there was no air friction. Or if you go to a lab where you suck the air. If you suck the air out, like they do in NASA, by the way, then you can replicate the experiment. Or you just go to the moon, or you can even do it on outer space, right? Actually, wait, outer space will be harder because gravity is lower. So you have to go to a place where there is at least a minimum amount of gravity and no friction, okay? All right, guys. So if you have any questions, let me know. I'm gonna finish the class right now. I'm gonna finish the recording.